Just a tiny bit. So my Wednesday and Thursday are the same time, but the Monday one had some complications, so now it's on Friday, same time. So hopefully if that fits in your schedule on Monday, it fits in your time on Friday, so 10 to 11. But now it is in PS, so the other two still in the same corner office, 146. The Friday one is in PSB 158, which is basically if you go in the front of Physical Sciences building, it is the room directly to the left, which is where the physics help room hours are. So the physics help room is basically, it's that room, and so they have these learning assistants, which are basically undergraduate TAs. They're undergraduates that took the class, did well in it, understand the content. They're going through a class right now on how to better support you all in learning. And so these students are actually in some of the other classes and work in the other classes, but they hold these office hours throughout the week. And at any time there is someone here with a white box, you can show up and get help with stuff. So this is just another resource. So you have my office hours, you have SARC, you have the physics help room, you have your TA's office hours. Please talk to them. They know their physics, they're graduate students, they've all gone through it. So you have a ton of different places to go. Please go to these places because these people, including myself, are here to support you. If you're having difficulty with a concept, if you're studying for a test, even if you're not having difficulty with stuff, you can just go in there, again, you can just be like, all right, what kind of things do you think are important for the test? Because they've taken these classes, they know what the hard stuff is, they know what's likely to show up on tests, because even though tests look different across classes, they usually have similar stuff. Anything, just like, please, use these resources, they're available, super flexible, there should be some time that works for you, somehow, some way. All right. Last time we finished up with flux, we finished up with Gauss's law. I told you all that the important things to remember from this were how to find flux, so how to do that E dot dA thing with the angle between them, and then how to find charge enclosed for various objects. So remember we did charge enclosed. Let me see if I can find the slides for it. Yeah. It's somewhere in here. Did a bunch of them, and then we found that the electric field due to a parallel plate is sigma over 2 epsilon naught. Sigma is the charge density. It's how much charge per area. So that's what we covered last time. We are done with Gauss's law. We're done with flux. We're not done with electric fields. We're still going to be talking about those, though we're effectively done with specifically just electric fields. Today, we're moving into the next one, which is electric potential energy. And electric potential, this date is way off. So electrical potential energy and electric potential, this is going to be very important for you all. This is something you're going to see a lot. You've already seen electric potential. It is called voltage. You've heard the word voltage. We're going to talk about it. We're going to talk about what it is, why it's useful, why it works, what it does, what it explains. So yeah, talk about electric potential and electric potential energy, two different things, but very strongly connected, as the words say. We're going to apply those to figure out basically how charges would behave, how they'll move. It's a different way for us to conceptualize how charges move. And we're going to identify how electric potential can be practically used in the real world, which is basically circuitry. That's what you all have seen. You've seen a battery. It says 6 volts, 12 volts, however many volts it says. That voltage is electrical potential, specifically a difference in electrical potential. So this is going to be very important for you all because understanding how a battery works is something an engineer should know. So, being able to explain what voltage is something all of you should be able to do in your careers moving forward. There's not a single major in here that shouldn't be a useful skill. Alright, with that in mind, I'm going to have you all remember some stuff from 2048 because we are going to use that. There's some concepts from 2048 from Physics 1 that you have covered that will help you understand voltage. So we're going to review if you remember them. If you don't, that's all right. We're doing this so you can check. So the question is, you drop a water balloon that has a mass of 1 kilogram from the top of the Physical Sciences building. The Physical Sciences building is much higher than 10 meters, but to make my life easier, I made it 10 meters. Hoping to splash your friend as he walks by. What value closest... which value below is closest to the speed at which the balloon hits the ground? So you drop it, 1 kilogram, 10 meters high. How fast is it before it hits the ground? Alright, I'm still missing, I'm guessing around 25, 30 people, so I'll give you all about 10 more seconds. Alright, in 5, 4, 3, 2, 1. Okay. So, first off, how do you solve this problem? Well, you look at it, there's actually two ways to solve this problem. I'm going to kind of highlight one of them because that's the one that I kind of want you all to recall more than the other, but both are good. The first one, which I'll tell you all is the one that is like still good, but not necessarily what I'm aiming for here. It's VF squared equals VI squared plus 2AD. If we want the final velocity, we know it starts at rest. We know the acceleration is g. We know d equals 10. So that's one way of doing it. The way I more so am trying to aim at here is that if you ever have a problem that you're trying to find velocity and you're given height and gravity, well, height and mass, you don't actually even need mass in this case, conservation of energy is what I'm trying to get you all to kind of recall. Conservation of energy, you start with some potential and that can be converted into kinetic. So conservation of energy is E initial equals E final. Initially, we only have potential. Remember, the variable for that is U. So we have potential in the form of gravity. I'm even going to label that it's gravity because we're going to start learning that there's different kinds. And at the end, we say it has zero potential energy because we say the ground is zero. We decide that. In fact, though, I'm just going to put it final here just to clarify that. Plus kinetic energy. Final. So you get delta U equals kinetic energy final. I'm writing delta U because remember height is a relative thing. You can call the center of the earth zero, you can call the ground zero, you can call anything zero. You get to define what that is, but it's mg height initial minus mg height final equals 1/2 mv squared final. So all the m's will cancel. You can factor out that g, so you get g, you get delta h, and you get that equals 1/2 vf squared. You do some algebra, which I'll leave to you all, and most of you all got it. You get roughly you get 14-ish, which is close enough to 15, approximately. Great. So that's the answer. I'm going to be referencing this stuff because the connection that we're going to be making is that if you understand this, if you understand gravitational potential energy, you can very easily understand electrical potential energy because they work exactly the same. The mechanisms why they're caused are different, but they can be used to explain similar things in a similar way. All right, next one is a concept question. Again, use whatever resource you want, but from Physics 2048, what quantity is determined by the change and potential energy of a particle which is acted on by a force? And then A is spring constant, B is displacement, C is acceleration, D is work. What is the, what I'm going to call this, variable that is equivalent to the change in potential energy of a particle which is experiencing a force? What can we calculate from that change? Alright, I'll give you all like 10 more seconds for this one. More of a memory than a critical thinking problem. Which one is responsible for it? Or which one can be determined by it? Alright, so 5, 4, 3, 2, 1. Okay, and again, there's not much conceptual, there's not much, how do you know that this is just an equation that you have to remember. Work equals negative delta U. That's work. That's the wrong one. Get out of here. Well, it broke. Anywho, I'll talk while it decides to be happy. There it is. It loves me now. So remember that work is the change in potential energy. So like in that last one, you could figure out the work that gravity did on that thing as it's moving. That's equal just to the change in potential energy. That concept is going to be really important because we're going to be using that as derivations throughout this section to just kind of, again, get to this idea. Remember, physics is all built up from fundamentals. So every single step here, we defined work at some point as force times distance, and now we're defining this new thing based on work, basically. Okay. How is work related to potential energy? Work related to force, talked about that. The only piece here that is missing is work equals force times distance. So work equals, remember the unit for work, it's capital W, that's the variable for it. So there you go, there's our equations. We're going to be using those to basically derive this idea of potential energy. Because, let's see, do I want to jump to the next one already? I'm not going to worry about that. Yeah, technically it is force time dot distance. I will put that in there. That's important. It depends on the direction it's going. Depends on the angle. Again, you can do force dot distance, and then you can do that cosine of theta. Not going to worry about that too much. Technically, you integrate it because that force can change over distance. So you could have a force. So in our case, we consider gravity to be pretty constant. So that's why we never really worried about integrating it. But you can imagine if you're in space and then coming toward Earth, gravity would increase as you got closer, 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 closer. So you would actually need to integrate that, or if your path is changing, that's where the integral comes from. Again, we're not going to actually need to use that integral here, but we will use it for the derivation, so pointing that out. Okay, so the next step then is we're going to use that concept. We know that the force due to, so we're talking about electric fields, so let's put the force due to electric fields in this equation. So we said that it's the integral. So this comes from delta UE is going to equal negative work. And we just said that work is equal to the integral of force dot distance. Here they use ds. That just denotes path that's moving. So this is the derivation. We remember work is force times distance. We know potential energy is the negative, change in potential energy is the negative work. So just plug things in. So force due to an electric field is a charge that is experiencing that electric field, so Q times E. You plug Q times E in here. Well, Q just gets pulled out, that's just a number. That's not varying. It's the one that's actually experiencing this change in potential energy, so it gets pulled out. You get the integral of E dot ds. Okay? We then, this is it actually, this is it, we're done. We're going to simplify this, it's in the integral form now. You're not going to see it very many times in the integral form. But basically, oh my goodness, that's just, there we go. Beautiful. You would just plug the electric field in here, you would integrate over the distance, and you can use this for any problem that you know the equation for electric field on. We're going to go to very specific examples of this, basically point charges, because that's what we work with all the time. But this is the derivation for potential energy. It's 2 steps, done. And then we're going to use this to derive some like specific case examples that you actually use for calculations. So if it looks complicated, please think on it more, think about it more, and just kind of work through that, because it's not too many steps here, and this connection between electric field and energy is going to be important. We're going to be using that moving forward. Okay. So the question here is, this is one of those just like, all right, we gave the equation, here's an example problem with it. We have a plane of charge which has the charge density given by nu. Nu is that little n thing. Remember, sigma equals nu. So they're both surface charge density. So, I want you all to practice this. I will even give you all the electric field. We just covered it. Maybe you don't remember it, but there it is. That's the electric field due to a plane. Using this knowledge that the change in energy is this, I'm going to give you basically all the pieces, and then I'm going to have you do it. Knowing that the change in energy is this, and remembering conservation of energy. So as this goes from here to here, it's going to go from no velocity to some velocity. So E initial equals E final. So delta UE will equal 1/2 mv squared. Spin a bit and see if, using all this information I've given you, can you find the velocity of the electron? Give it a whirl. And I'll even put over here, delta UE is that same equation for the last time. It's negative Q times the integral V dot ds. Challenge yourself, see if you can do this. Talk to your neighbors around you if you're stumped. But all the pieces are there. I gave you every single equation, now it's just kind of working through them. See if you can do it. Spend some time. And you're going to leave it all in terms of, well, yeah, you can even put numbers in if you want to. I recommend leaving it in terms of variables as long as you can. Just because you have to write more numbers if you put in the numbers. So save yourself some writing. And it's unfortunate that not too many of the questions I give you all actually have you doing integrals. So this is one way for you all to get some practice doing that, because you are going to need to know how to do integrals with real world situations in your engineering courses moving forward. That is a skill, that's why you take calculus. Alright, I'm seeing writing's pretty much slowed down. So I gave you all the pieces here. Basically, this is how we're solving the problem. And then it was kind of just working backward. So I wrote all the things kind of randomly on here, because in my head I was doing the, well, what do you need to actually solve this? So to start off with, it's a conservation of energy, because it starts with some energy here, and we're going to talk more about this potential energy, but we just covered that it gets some potential energy. There's some difference in the field. So then we're like, all right, great, difference in energy. This is just like a ball falling, but why is it falling? It's falling because of because of electric force, not gravitational force. So exact same problem we started the class with, but instead of gravitational force, it's electric force. Then I gave you the equation for how to calculate that difference in energy. And then you're like, okay, Q, great, got that. E, don't know what that is. Distance, that's Z on this picture, so I know Z at least. And electric field, I then gave you because we're like, okay, we need that to solve that. All that to say here then is what it's going to look like. All the things plugged in. So you plug in the electric field, sigma over 2 epsilon naught. We know that the charge is going to be a charge of an electron, so it's negative. So we put that negative in there. You integrate it. Remember, this is a special thing about the capacitor or the parallel plate. It has no dependence on distance, so this is literally just a number. It's a constant. You can pull a constant out of the integral. You're integrating from 0 to z. You pull it out. The distance is just going to be z. It's negative 0 to negative z, It starts off at z and it goes to 0, so you get a negative again, so we actually return that. So there's our delta energy. And then, yeah, you plug that into the 1/2 mv squared and you're done. It's algebra at that point. So this is just kind of an example of what a problem like this would look like. This one we use the integral. Again, some of them you're not going to use. I say we used the integral. We didn't really use the integral. It was a constant. So you didn't actually have to integrate anything. This integral basically turned into this. Q e times d. Because it was a constant. Yep.
Whenever you set the equals to each other, wouldn't the 1/2 cancel out?
When the 1/2 here cancel out? Oh, did it not cancel out? Oh, that's my bad. Yeah, good catch. Yeah, there should not be a 2 here because there's a 2 here, 2 here. Excellent catch. But everything else should be pretty good. All right. So there you go. That's just an application of it. Really what I want you all to take from this is the same thing as conservation energy that you've seen before. This is just energy coming from an electric field. And we're going to, again, talk about that a bit more. So, here's a more simple example. We have 2-point charges. They're positioned on the x-axis. One is at the center. It doesn't really matter whether it's positive or negative. But one's here, and one's going to be at xi. How much work must be done to move the charge Q2, so this is Q1. How much work must be done to move it from x initial to some spot which we'll call x final? Well, work equals the integral of force times distance. So then we're just going to have to plug in what force is. Remember, force is K Q1 Q2 over R squared. This is just the force due to an electric field. The force is always going to be, so R is this way, or ds. ds is this way because that's the direction it's moving. So it's from xi to xf. And the force, I guess it's depending on whether it's positive or negative. We'll just make them both positive to make our lives easier. So the force is going to be the opposite way. So at every point, so this is going to be this, we get our ds, and we get our cosine theta. Cosine theta here, theta equals 180. They are opposite in direction, it's the angle between them. So this equals -1. Equals -1. And I'm going to change this s. I guess I could just, I'm going to change this s to an r. You can change it to whatever you want. Basically, ds denoted a distance, r denoted a distance, so they represented the same thing, so I just basically translated it. It's like translating from another language, they both just meant the same thing, so I just changed the variable to reflect that. Okay, so I could have originally put here dr, I could have originally put here on the bottom s, it's all the same thing. You just have to keep in mind that variables, just as long as you know what they mean, if they mean the same thing, they are the same variable. That's the long and short there. Okay, so we write, I lasso this. Today's a very conceptually heavy day. I'm going to try to present this concept in as many kind of different ways as I can, and at varying levels. So the first one was kind of a more complex example. This is a bit more of a simple example, and eventually I'm just going to give you the equation, and it's up to you whether you want to actually understand all this stuff, but if you do, it's going to help you out in the long run. Okay, so we just integrate. Equals, pull out the k, pull out the q1, the q2. The integral of dr over r squared is just, and there's a negative here. Just need to know how to do an integral, so the integral of 1 over r squared is going to be -1 over r, so it cancels out again. And we need to evaluate this from xi to xf. So you get this, you get k q1 q2 over r, evaluated from xi to xf. So you get k q1 q2 over xf minus k q1 q2 over xi. There's your answer. Okay. Lots of steps that happened there, but again, it all just basically came down to force times distance, or force times the ds. You integrate over that ds, which I changed to dr because r is just traditionally what we use there. And you return this expression, which looks a little complicated. Here it is in more writing. It's the same exact problem, but written out. Please look through that. The interesting thing is what happens if you make your x initial be infinity. That is how we're going to return the one that you are going to see the most often. So instead of starting our charges at two set distances that actually have a value, start it instead at infinity and then bring it in. If you start at infinity and bring it in, the initial is going to be infinity. If you divide any number by infinity, you just return 0, so you just get the first term. Or, in this case, they actually took it to infinity. So this one's actually the opposite problem, where they started it at some point, they took it to infinity, and so that one becomes x, and then they just took the magnitude of it. So, all that to say, all that work, this is the potential energy of two charges. If you have two charges together, this is the potential energy not of each charge, but of the entire system. And again, we're going to get some practice with this. I'm going to give you all an example problem, which is going to kind of help you actually face what that means. But basically, imagine it this way. How much energy would it take for me to bring a charge from infinity to a point with nothing around it? It's not going to take any energy for the same reason. How much energy would it take for me to move this water bottle from left to right? 0. Why? Or how much work would I need to do is a better way of putting it. How much work do I need to do to move this bottle from right to left? I heard 0. People are comfortable with 0. The reason I want to remind you all is what forces do I have to push against to move it from here to here? None. There are no forces to move it from here to here. Technically, obviously, my arms having to do work. It's more complicated than that. But if you're moving a charge, if I just plop a charge here, I didn't have to do any, there's no other charges, there's no other forces acting on it. If this is in vacuum, for me to move a charge from over here, all the way over here, there is no other charges. Therefore, it's experiencing no other force. I can move it easily with no problem. Does that sound okay? Does that make sense to everyone? No forces, no other charges to make forces. So moving one charge. No other charges to cause force on Q1. So here's my Q1, here's my Q1. If I draw my free body diagram, I already drew my free body diagram. There's no forces acting on it. There's nothing I draw on it. F net equals 0. It's free to move it around, therefore, the amount of work I have to do, integral of f dot dr, if f equals 0, work equals 0. I can move a charge around. If it's by itself, nothing's around, no problem, easy. Once I move the second charge, all right, so we've moved our first charge to some spot, because this is how we're getting the energy of a system. We imagine we build the system from nothing. So originally we had nothing, we brought in a positive charge. That took no work, because I didn't have to push against anything. Now, we have our first charge here. So this is our charge 1, now that exists. We're going to bring in our second charge, because our system is 2 charges. And we're going to bring that from infinity to some distance r. The question then comes, how much work do I have to do to move it from that infinity distance to that distance there? That is the integral I showed here. That is what we calculated here, was how much work do you have to do to move a charge a distance? We get this final equation. Well, let's go ahead and put that equation here. So work here is going to equal K Q1 Q2 over X final minus K Q1 Q2 over X initial. Here is my X final. Here is my X initial. It started, and where we're going to set X initial is at infinity. Because we are taking it from infinite, we're making our system, so there's nothing, we put one charge there, great. We take another charge from infinity, bring that one in. Again, imagine you're building this thing. So in that case, the second term goes to 0. Because if you divide it by infinity, as the limit goes to infinity, that's what the math people are very strong about. Infinity is not a value, but in physics we just kind of put it in there and make that term go to 0. Make it go to 0, and this is what you return. This is the energy of the system. Work 1 plus work 2. So work 1 plus work 2 equals work net. Work 1 is 0. Work 2 is that. Work net is just going to be that value then. Okay? That is the energy of a two-particle system. The energy of a particle by itself, 0. It has no potential energy. Basically, a charge. Think of it the same way. My water bottle has no potential energy if the Earth didn't exist. There's no potential energy until I introduce a second body with mass. Now that there's a second body with mass, there's a potential energy of the system between my water bottle and the Earth. So whenever you all were doing potential energy problems, that was an assumption that the Earth existed. If the Earth didn't exist, you can't do your thing's not going to fall. So try to think on that a bit more, but here's finally our kind of formal definitions, all characterized. Electrical potential energy is the potential for a system to do work due to electric fields. So you had gravitational potential energy. That was the potential for a system to do work due to gravitational fields. Now it's electric fields. The variable we use is this U, same thing you use for gravity, but I put a sub E to denote that it's due to electric forces. You need to, when you're doing these problems, make sure you're labeling them, because now we've introduced a different kind of potential energy. They're caused by completely different things, but they're going to have the same kind of mathematical use. Unit is joules because it's energy. So any kind of energy is always joules. This was our formal or general expression where you have that electric field. Remember, Q times E is force times that. There you go. And this is when you have 2-point charges where that's the distance between them. All right. Basically, if I want you to take away one big thing, if all this isn't making sense, the final takeaway is that when you put charges together, you get a potential energy of the system because they either want to be closer to each other or they want to be farther away. You put two positive charges, they want to be farther away. You put a positive and a negative, they want to be closer. There's a potential energy in that system. The second you let those charges go, they're going to move. And the same way, my water bottle does not want to be here. It has potential energy. I drop it. It wants to move. That's the basic idea. Little complex sounding. Took a lot of steps for us to kind of get to that. But I wanted to kind of give you all the depth if you're interested in all the derivations, because that may help some of you. Otherwise, we can just talk more, and that'll hopefully be helpful. Okay. There you go. We're going to start with something easy. Build some confidence. If I have two charges that are both positive, what happens to the net potential energy if I double the distance between them? Showed you all the equations on the last thing, so you can use the mathematical thing there to figure it out. And then you can check your answer by just imagine the same thing with gravitational. What happens to the energy if I double the distance my water bottle's away from the Earth? Same exact, make those connections. go, about 5 more seconds. All right, in 5, 4, 3, 2, 1. All right. So what happens to the net potential energy? Well, we can use our wonderful equation that I showed you on the last slide. So it's net potential energy. So we're going to use the equation for net potential energy. It's 2-point charges. So we're going to use the equation for 2-point charges. And that equals K Q1 Q2 over R. So this is kind of our initial. And let's go ahead and write our final. Everything stays the same, except now RF equals 2RI. So we plug that in here, KQ1 Q2 over 2RI, initial. So you see here that my final, this should be a final, our final is 1/2 the value of that one, of the initial. I saw some people put quarters. I saw a couple of people put halves. Reminder to you all, we're not using the electric field equation. So the electric field equation for 1 had that squared term. This is not squared. This is just on the bottom by itself. The other reminder is that this is the net potential energy of the whole system. So it's not that one of them gets half the energy and the other also gets half the energy. The whole system loses half the energy. And then doubles, yeah, just going to make certain you're putting in the right place to the denominator, so it's going to half it. Okay. All right, I'm going to maybe jump at, I'm going to I guess I'll quickly talk about this. This isn't a huge deal here. There's not too much to kind of write here mathematically, but this is just kind of the idea. This is conservation of energy. If you gave it some initial kinetic energy, so each one had some initial kinetic energy, and you launched them, so you're launching at each other, velocity, kinetic energy. What you can do is you can graph that K, Q1, Q2 over R, and they are going to repel each other the second that kinetic energy, that initial kinetic energy they have, equals a potential energy. So potential energy is going to grow the closer they get to each other, until finally all the kinetic energy has been converted into potential energy. At that point, you no longer have kinetic energy. You now have potential energy stored up, and because you're not holding them there, they're going to go back the way they came. Kind of like a spring. So this E mechanical here is kinetic energy initial. So this is kind of one way of visualizing it. You both have a picture, and then you have a graph here. When the initial kinetic energy equals the potential energy, that is the value at which point they'll repel. Same thing on the other end. If you have two attracting charges and you push them away from each other, same thing. They're going to push a certain distance away, and at some point then they'll attract together. Yeah, so there you go. And that's the same thing. This energy here is kinetic energy initial. It's a little confusing because it's E, which you may think is electric field, so that's why I wanted to clarify kinetic energy. Okay. Nice thing is this is independent of distance, or not distance, is independent of path. So a reminder, you all saw this in Physics 1. Basically, the long and short of it is you can do a conservation of energy problem no matter what the path looks like. You can do a conservation of energy problem if you have a car, and this is the power of conservation of energy, is we can use it to solve problems that would be a nightmare to solve otherwise. So say you had a car going down a hill. There's my car. Beautiful. Sure, I could integrate the force over distance and find the final velocity down here, but that's disgusting because this path is curved and gross. I could even have a path that looks like this, and you can just imagine trying to find the force at every single point that it experiences due to gravity. You change at every single point. It's disgusting. The nice thing about conservation of energy is we don't care what path it takes. It's a conservative force, which basically, that's what it kind of shows here. It doesn't matter the path it takes. And so you can say you can say energy initial equals energy final. It does not matter the path it takes. You can say delta UI or delta U equals delta KE. And you can use that same one no matter what that path looks like. This is why we talk about conservation of energy, because it's a very useful tool. It's even an important concept just in general. It's one way of understanding the universe. Basically, a rule of thumb is that things want to go to the lowest potential energy state they can. That's how you can almost describe, no, that's how you can describe every single thing we understand in the universe currently. If someone asks you why something does what it does, you can honestly just say, because it's going to the lowest energy it can. The lowest potential energy. The trickiness, and this is just an interest topic. You don't need to remember this. But you can get these things called wells, where basically you have some object and it travels down, and again, you've seen this with gravity, but this also extends to charges. This extends to why charges get trapped and why when you heat things up, they kind of go away. So it falls down here. If it does not have enough kinetic energy, it will actually maybe a better one is like this. We do this, and then we put a bigger hill here. It's going to stay in this well, even though there's a lower potential energy on the right here. It has to get enough energy to get over that hump. So this is one of the explanations what catalysts do. Catalysts help reduce that hump. Help you explain why chemical reactions occur. You put enough energy in, and it wants to get to that state, but you got to give it a little bit of a kick first to get it going. So, anywho, conservation energy, super important in every single concept, every single class you're covering, it's going to be useful. Okay. Whew, a lot of stuff. We're going to finish with one last thing. I am not going to have you all answer this clicker question yet because it's a little tricky. I'm not going to grade you on this clicker question. I am going to have you do it. I will give you the technique for doing it. So remember, you're going to use the same technique I did for the 2-point charges. You are going to build this system. So I take one charge. So initially we start with nothing. You start with nothing. And then I bring in a positive charge from infinity. There we go. There it is. That's step 1. Now I need to bring in a second positive charge. That's step 2. Bring in a second positive charge. How much energy is stored in the system with 2 charges? The next one is I must now bring in a third charge into the system. What forces need to be overcome? And the reminder to you all is the path does not matter. So, I don't know, just think about it. Give it a whirl. Stretch your brain a bit. If you have 2 charges, what happens to the net potential energy if I bring in a third one? Does the energy double? Does it triple? Does it stay the same? Does it quadruple? Think through that idea of what work do I have to do to bring in that third charge? I've already told you what it takes to bring in 2 charges. What does it take to bring in a third one? So on, and then we can extrapolate what would happen when we brought more. Reminder, it's independent of path, doesn't matter what direction, just matters where it starts and where it ends. My other hint to you is when you're doing this last step, just do a system at a time. So ignore this one, and just worry what it would take to bring this one here if this is here. And then ignore the other one, and imagine what it would take to bring this one here if this one here. It's a summation, so you can totally treat those just like we've done before with forces. Look at 2 pairings at a time. I'm not going to open it because last time I did this, pretty much it's a little bit tricky. So that's why I'm like, if I ask this, I'm going to pretty much guarantee that most people won't get it right. Maybe you'll get it right. But I'll be kind and not make you all just miss points for it. I'll open it at the end of it after we've kind of worked through it. So you'll still get credit for thinking about it. After we've talked about it more and I've given you more support to getting the right answer. So at the very end, I'll open it up. I won't do the very last step. I'll leave that for you all, and that's what I'll grade you all on. so hopefully you spent some time thinking about it. If you didn't, well, I can't force you to think, but please do in this class think as much as you can when I give you these opportunities, because this is what you're paying for. Okay, so I'm just redrawing all this to give myself a little bit more space. Same picture. So step 1, what's the work done here? 0. What's the work done here? Hear a bunch of like mumbling, not as confident as 0. There you go. KQ1, Q2 over R, because this is R. Again, it matters where it finally ends up. It doesn't matter where it started. Well, we put it at infinity, where to start from. All right, this last one, so that's work 1, that's work 2, work 3 is going to be, so I'm going to first, remember what I told you all, let's just do one, so we're going to kind of ignore Q2 and just worry about the work it would take to move 3 here with just 1 there. So that's going to be KQ1, Q3 over R. Same exact thing as a step 2 here, so if you understand step 2, great, we just did that. Now, we ignore Q1, and we find the work it would take for Q2, for these 2 systems. Q2, Q3 over R. The reason they're all over R is because this distance is R, and this distance is R. And you may be like, well, that's weird. This came at us like this one. Sure, makes sense. It's a flat line. This one, I came from over here, though, and I came to here. Why am I using R and not like this distance? It's because it only matters the starting point, the end point. It doesn't matter the path you take, doesn't matter where you're coming from. It matters where you start from, where you end, and the distance between the things that you're having to work against. So, all that to say, here is what it is. Work net will be this addition of these 3. Work 1 plus work 2 plus work 3. Now I will open up the question to you all. How does the net potential energy compare? What happens to the net potential energy when I brought in the third one compared to when it was just the 2 charges? So how does the system, how does work net compared to, for 3 charges, compare to, well, I'm going to say work net, energy net, because remember the amount of work you have to do is equivalent to the energy of the system. Work you put in, it's stored as energy. No, so the sign's not going to change. It's all just going to be how they'll all be the same sign. Yeah, so work does equal the negative potential energy. Yes. Make certain you're checking that your math is right. Yep. Yeah, you are not trying to figure out delta. This. No, you're not trying to figure out how the energy increases or decreases. You're trying to find the ratio. The ratio between U net with 3 charges and U net 2 charges. I want to really clarify that. Not addition and subtraction. Ratio. Because that's the words I use here. Is it double? Does it triple? Does it stay the same? All right. I'm going to close it out in 5 seconds. 5, 4, 3, 2, 1. All right. So let's go ahead and check real quick. We're right at the end, but I'll give you all the answer. If this is the energy of this one, so this is what it is for 2 charges. For 3 charges, it's this plus this plus this. So how many of them do I have? 2 of them or 3 of them? 3. It triples. Because it is 3 times as much as W2. If this is 1, this plus this plus this is 3. Triples. And it exponentially increases the more charges you add to it. Have a wonderful weekend. Yeah, what's up?
I had like an issue with my lab class, and I was able to change it
Yep.
to a different section. But I was worried about like I wasn't able to go to the last two lab or